So kinematics is the study, or you can say the physics of motion. So motion of a particle or a body, okay, or an object or whatever is described by equations of motion in this. Which express how parameters or variables like displacement, velocity, etc. You say evolve with time. Kinematics does not deal with the cause of motion. So it does not deal with force, right, work done, energy, etc. All that comes in different chapters of physics, like Newton's laws of motion, work by energy, etc. It just deals with the motion itself, describing the motion by representing it by equations which express how these parameters evolve with respect to time. Okay. Now, in this particular section, which we call kinematics, we are only actually studying a section of kinematics, which is called particle kinematics. So I'll explain what we mean by this. Okay. Particle kinematics is the description of motion for a particle, and you know that a particle is basically defined as a point mass. So something that does not have any appreciable volume or surface area or anything like that, but has only mass, that is a particle. Okay. However, even the motion of rigid bodies or objects can be expressed in terms of particle kinematics, provided they are not rotating. So this is something very important, and I'll explain this with examples. Okay. So such motion is called pure translation. Okay, so I'll elaborate further on that point, but just go through this section once and make sure you absorb this information. You can write down the key points if you like. Okay.
Sir,
Yes. Yes, Beta, tell me.
sir, can you give a revision worksheet on integration?
Yeah, sure. Have you completed the questions in the module?
Yes, sir.
Okay, very good. Then I will be sending revision worksheets for actually entire calculus. Okay, so that will include problems of integration also. And in any case, you know, what you will see is that we will be doing like plenty of application of calculus even in kinematics. So from this point onwards, calculus will be there in everything we study. Only thing is like, in any one given chapter, there won't be all the aspects of calculus involved. Like, in kinematics, for example, there won't be too much of maxima minima kind of concept. It will be just differentiation and integration. Okay, similarly, in Newton's laws of motion, there won't be too much of calculus. In fact, hardly any calculus, more of vectors. But next chapter after that, work by energy, there'll be some calculus again. So, but more or less, everything we are studying, it will have both applications of vectors as well as calculus at some level. So,
Sir, and it would be great even if you could include some problems on applications of maxima and minima in the worksheet.
yeah, there will be some revision problems.
Yes.
Have I given you people the list of the reference books yet? No, no.
No, sir.
Last lecture, I did not. Okay, so today at the end of the lecture, I will give you some additional reference books names also. So once you start referring to them, you will get some additional questions there also. So what you should do now is like every week you should keep aside some time, like maybe a couple of hours, for doing some revision questions in the previous chapters that has happened. So vectors and calculus, so that you never get out of touch with those things.
Yes, sir.
So in that revision time, you should pick up, like typically you can pick up fresh problems instead of revising the problems that you have already done from the worksheets before. So we will be sending you, we'll keep sending you some revision worksheets also in every chapter from time to time. Okay, so this part is clear. Na? So now we will use a very technical term called translation. Okay, so in other words, so therefore, when a rigid body, you all understand what a rigid body means. Basically, a rigid body is, like you can say, a collection of particles which are stuck together in such a way that they are rigid in structure. Its shape, size, etc. does not change. So it's a many particle body, okay? But such that the particles cannot move with respect to each other. I mean, at a molecular level, everything is always moving. So even in solid objects, there is vibration of molecules happening. But at a macroscopic level, we don't really observe that. So a rigid body is a body such that when you observe it macroscopically, you don't see any changes happening within it in terms of dimensions or shape, size, etc. So you can imagine that the particles that constitute that body are fixed with respect to each other. They are rigidly attached to each other. So that is the meaning of the term rigid body. So therefore, when a rigid body is in what we call pure translational motion, I'll explain what pure translational motion also means. Okay. So this is an important technical term for us, translation. So pure translational motion. Okay. It can be treated as an equivalent particle. Okay. To describe its equations of motion. So translational motion, what does that mean? Let's understand. So pure translation is the type of motion that does not involve any rotation. It doesn't necessarily mean, motion along a straight line. A rigid body can be moving along a curved path also, but it should not be rotating or spinning. Okay. So, for example, if a block is moving in such a way that it's going in this kind of path, but as it is moving, its orientation always remains the same. This is pure translation. Okay. As opposed to this, for example, if we have a rod which is hinged over here and is going in rotational motion like this, such that the axis of rotation is always fixed. So this is an example of, in fact, what we call pure rotation. That is rotation about a fixed axis. So this is not in the category of pure translation. It comes outside because it involves rotation. Then another type of motion, which is the most general type of motion that you observe for rigid bodies, is this kind of thing. You know, if you throw something and it's going like this, like I'm showing you here. Like typically, if you take an object which is kind of linear in shape, like a rod or a pen or something, and you throw it in the air, it's not going to go like this. It's not going to go like this. It's typically going to go like this, such that while the center of mass is describing that projectile kind of path. Okay, but what is happening? It's also spinning about the center of mass. So this type of motion is called a combination of translation and rotation. The center of mass is going in a translational path, whereas at the same time, simultaneously, along with the translation, there's also rotation happening about the center of mass. So that's another type of motion which is not in the category of pure translation. So if an object is moving like this, that it's moving, and while it is moving, it's also spinning. So, at any point of time, there is a velocity that the center of mass has, and about the center of mass, there's also rotation that is happening. So this is a combination of rotation and translation. So when these two types of motion are happening, what you can see is that different particles within the rigid body have different amount of displacements, velocities, etc. Here, for example, you can see that this particle is describing this kind of a path, whereas in the same amount of time, this particle has described this kind of path. So it's traveled a different distance. So obviously the speed is different. So obviously the instantaneous velocity is going to be different. So all the particles are not having the same parameters. Okay. Whereas when we have pure translation, all particles have identical motion. They're all moving together in such a way that they have identical motion. So therefore, in case of pure translation, the motion can be described by just writing equations for the center of mass of the body, treating the entire body like a compressed particle at the center of mass. Okay. So therefore, the motion can be described as the motion of an equivalent particle, as if you compress the entire rigid body into a single particle. Whereas in this case, you cannot do that. We cannot treat the body as an equivalent single particle for its equations of motion. So this type of motion we will study in a later chapter. So these types of motion will be studied in the chapter called rotational mechanics, which we'll be doing a little bit later within our class 11 syllabus only. But this type of motion is what we'll be doing in the kinematics chapter. Okay. Hence, actually, the technical word for this kinematics chapter is that it is particle kinematics. Where it is rigid body kinematics, we will be dealing with in rotational mechanics, and another name for the term rotational mechanics is rigid body mechanics. Okay. So anyhow, this is just like an introduction to the subject, that you should know this thing from before, that what we are going to study in this chapter, which situation we can apply it in and which situation we cannot apply it in. So we can apply it for any rigid body, any large object, a comet, a planet, even something as large as that, even a galaxy, but provided we are describing the motion such that that object is not spinning, which is obviously not the case with a planet or a comet. Okay, they do spin. So we won't be actually technically be talking about objects like that. But even a large size rigid object like a vehicle or something, if it is not spinning while it is moving, then we can describe its motion completely by treating it like an equivalent particle located at its center of mass. So we can apply the principles of particle kinematics to use those kind of equations to represent its motion.
Sir, can you please scroll down?
Yeah. So this part is done, na? The part above.
Yes, sir.
Okay, so these points are clear, I hope. If anybody has any question in this, you can clarify with me. Okay. Okay, so now having understood this thing, let's get down to the parameters that we use to describe particle kinematics. So, just keep in mind what we mean by the term kinematics here now is particle kinematics. So even if we are describing the motion of a large size object, we are treating it like effectively like a particle. We have to visualize the whole thing that way. So first thing we will do is we'll learn about the parameters. Or you can say the physical quantities used to describe kinematics. So the first term that we use in kinematics actually even in Newton's laws and whole of physics in that sense, especially mechanics, is the term reference frame. So reference frame is very important because it is a sort of framework with respect to which all measurements are made. So what does the term reference frame mean? frame typically means it is a system of axes. Okay? It's a system of coordinate axes. Or you can say a coordinate frame, which consists of an origin and mutually perpendicular XYZ axis, or what we call the rectangular Cartesian coordinate frame. So a system of coordinate axes used to reference the motion with respect to. So the measurement of motion measurement of all the parameters are done in reference to that frame. So you'll always hear the term reference frame in mechanics. So in simplest term, what is a reference frame? It is just that the person who's writing the equations of motion, he or she has to decide on some system of axes and some particular point as the origin, so that they're able to write the equations with respect to that reference frame. So that is what is called the reference frame. Now, once we decide our system of reference, then we can start looking at things like position, displacement, velocity, etc. So the next thing is the position. Okay. And here by position, we will mean the vector definition of position. So we'll call it position vector, okay, for a given particle. So from this point onwards, we represent the position of a particle. And remember, even if you're talking about a rigid body in this chapter, we are treating it like an equivalent particle, which is located at its center of mass. So this is our reference frame, standard XYZ mutually perpendicular axis, where remember XYZ axis orientation has to follow your right hand palm rule. That is the rule that I cap cross J cap is equal to K cap. So in my diagram, if the X axis is pointing towards the right hand side, as I've shown, Y axis is vertically upwards, then Z axis is coming out towards me. It should not be going into the plane. Into the plane will be the negative Z axis. Okay. So where they meet, that point is the origin. Now, if I have a particle which is at this point P, so for a given particle E located at some point, let's say X, Y, Z, with respect to that reference frame, the position vector. So from now on, when we use the term position also, by default, we mean position vector. It is given by a symbol R. And that R is nothing but the vector originating from O and terminating at the point P. So it is not a free vector like other vectors we have studied till now. Okay, it's a fixed vector. We cannot move it around. Okay, it starts from the origin and its arrowhead is pointing exactly to the point where the particle is located. So this vector is nothing but xi cap plus yj cap plus z, where magnitude of this will become the distance from the origin. Okay. And typically in SI system, okay, or centimeters in CGS system, or it can be in kilometers, miles, etc. in non-standard systems. Okay. It has the dimension of length. So we will always refer to the position of a particle by the vector definition in general from now on. If the motion is restricted to only one axis, then we can reduce it to just one component of the vector. But in general, we will refer to it as the position vector. So now see, the moment we have defined position, one other thing that you can immediately see is when do we say the body is in motion or when the particle is motion versus when it is at rest. If the position vector is remaining constant, that is that vector r is not moving at all, neither of the three components x, y, z is changing with time, they're all constant, then we will say that that particle is at rest. Whereas if that position vector is changing with time, it's variable with respect to time, then we will say that the body is in motion. So that is how we define the two terms rest and motion. That's an automatic definition that we now understand for the two terms rest and motion. If the vector r is constant with respect to time, then the particle is said to be at rest. Okay, but of course that thing rest is in that frame. In some other frame, it might be in motion. So for example, if my reference frame is fixed to the ground, okay, that is the surface of the earth, and in my reference frame a particle is not moving, then I can only say it's at rest in my frame. Okay, somebody else might be standing on the moon or might be orbiting the earth in a spacecraft, and in their reference frame, obviously that particle is not at rest because the surface of the earth is moving. So even rest and motion are relative terms. In one reference frame, an object which is at rest may not be at rest in another reference frame, which is moving with respect to the first. So everything that we describe in kinematics is always with respect to a reference frame. Hence, the starting of it was with the definition of reference frame. Whereas if R is changing or if R is varying with time,
So can you please scroll up?
yeah, sure. This part only, no?
Yes, sir.
Just a second. Okay, so written this down now, people.
Just a minute.
Okay.
Sir,
Yes.
sir, can you give example of reference frame?
Example of reference frame just means this beta, that when we are writing the motion, I mean equations of motion for a given body, na, we have to decide and select some point as our origin and some particular direction as x-axis, then perpendicular to that as y-axis, like that, you know. So for example, suppose we are, let's say we are standing on the terrace of a building, okay, and from here we throw a ball like this. So that ball goes in this type of a path. Now it's up to us, you know, like somebody else is observing this. So that person might decide that, okay, where the ball starts from, that is only his origin. So in that case, the reference frame will be where the ball starts from. And the person might decide that, okay, where the ball ends, that is also his origin. So in that case, the reference frame will be where the ball starts. And the other person might decide that, okay, vertical direction as x-axis, horizontal direction as y-axis. So it is completely up, up to the person who's writing the equations of motion, that how they select the origin and how they select the system of axis. Only thing is, in the axis system, they have to follow the standard, rectangular Cartesian system, where the three axes x, y, z should be mutually perpendicular, and they should be such that they are in agreement with the right hand palm rule. That is that I cross j is equal to k cap, like that. Is it clear, beta?
Yes.
Okay. Now the thing becomes complicated later when we study something called relative motion, where we'll see that two observers, they might have reference frames that are not only different, but they are moving with respect to each other. So, like let's say we are again going back to that example that somebody has thrown a ball from the top of a terrace. Now another person observing it is, instead of being stationary on the ground below, that person is running on the ground, or they are moving in a vehicle. Then their reference frame will be moving with respect to that building. So that will complicate matters a little bit more. And there we'll have to use the concept of relative motion, which will be the last part of kinematics when we come to that. Understood the point now?
Yes.
Okay. So reference frames can even, two different reference frames can even be in motion with respect to each other. Okay, so that is the whole point about it. Okay. Now the next thing that we will look at is the first important parameter for describing the motion, and that is called displacement. Now we will see that there will be like a single formula for displacement, which will make it a very simple thing compared to the wordy long kind of definition that you studied of displacement earlier in class 9-10. So the common meaning of the term displacement, how we describe it in everyday language, we say it is the shortest path joining the initial and final position, or is the straight line joining the initial and final position. Here we will come with a vector definition of displacement. Okay, so we will think of displacement as a vector quantity now, and we'll denote it with the symbol S with a vector arrow. Okay, so the displacement is a vector joining the initial position with the final position for the given time interval. Okay. If we don't know what time interval we are talking about, then the term displacement doesn't make sense. For a moving object, if I just say what is the displacement, it doesn't make sense. We have to specify the displacement from what time to what time. Okay. So it's always for a given time interval. So now let's visualize it, with respect to our reference frame, and you'll see that we come up with an even simpler definition in terms of vector algebra. So let's say in a certain time interval t1 to t2, the particle in question is moving such that initially the particle was located here. Okay, so this was at time t equal to t1, let's say. So its initial position vector is this. So we'll write this as r1. So now After some time T2. Now T2 is greater than T1. Let's say it's T1 plus delta T. So during this interval of time, let's say the particle has taken some whatever kind of path, some arbitrary path, and reached here. So now at this new time T2, this is where the particle is located. So its new position vector is this one. So regardless of what the path is, the definition of displacement is very simple. It is in this time interval from T1 to T2, the displacement is nothing but the vector, or you can say the straight line, but here it's a vector which has a definite direction from initial to final position. So it's this vector. It's the vector starting from the initial position and its arrowhead should end at the final position. So this is the vector that represents the displacement. So S for the time interval T1 to T2, it is the vector joining the head of the initial position R1 to the head of R2. So in terms of vector algebra, you can see what this vector is. This vector in this vector triangle, what is the relationship between the three vectors? R1 and R2 are drawn from a common origin and S is pointing from R1 to R2. So S is basically what? It is R2 minus R1. Or we can generalize it by saying that in a certain time interval, S is equal to the displacement vector is equal to the change in the position vector. That is the final position vector minus the initial position vector. So now we have a very, very simple single formula definition of displacement. The displacement vector is the change in position vector, or it is delta R, or it is R final minus R initial. It is R2 minus R1 for a given time interval T1 to T2. So you can see that again, magnitude of displacement is in meters or centimeters or kilometers, miles, whatever. It has dimension of length. And anytime there is motion happening, there will be displacement. So one thing you can straight away understand is that the displacement vector is independent of the path, which you can understand from the diagram. The dotted curve represents the path of the particle, and the displacement may not have anything to do with it. It's directly the line joining the initial with the final position. Okay, so just make a back. Okay, so for example, we have something like this, that particle was located at time t equal to 0. Okay, now every alternate second, it moves by 0.5 meter along the x-axis, followed by 1 meter along the y-axis. Okay. By every alternate second, I mean in every 2-second cycle. Okay, so it goes in this kind of thing, like it goes like this, then like this, then again like this, like this. Okay, then again like this, like this. Okay. So every 2 seconds. So this is where it was at some time t. Then this is where it is at t plus 2. Then this is where it is at t plus 4. Okay. So every 2-second cycle, it goes in like a stepwise structure like this. Okay. So we have to find its position at t equal to 4 seconds, t equal to 8 seconds. And secondly, we have to find its displacement from 0 to 4 seconds, 0 to 8 seconds, and 4 seconds. So just try out this question, people. It's more like a question of vector algebra actually, but yes, very good, Kirti, that's correct. Now for the displacement partner, we'll also find the magnitude of the displacement. The displacement as a vector quantity as well as the magnitude of the displacement. Okay, so in this question, what we can do is, one is we can do a visual representation of the whole thing. So we can start by visualizing the coordinate frame as a standard XY. So the particle is located somewhere here, let's say, at t equal to 0. Its coordinates are 2, 4. So its initial position vector is like this. At t equal to 0, its position vector would be 2 I cap plus 4 j cap. Okay. Now its displacement from 0 to 2 seconds is how much? It is half a meter along the x-axis plus 1 meter along the y-axis. Okay. Then its displacement from 2 to 4 seconds is again the same, and so on and so forth. Okay. So we'll see something interesting, that it keeps moving along this straight line. It's actually, in fact, going along a straight line path. I mean, not along a straight line path, but if you compare it, it's on this particular straight line. So you can see that the position at 2 seconds will be equal to the initial position plus the displacement from 0 to 2. So that will be equal to 2.5 I cap plus 5 j cap. So its position at 4 seconds, you can write as position at 2 plus the same displacement. So 3 I cap plus 6 j cap. Like that, the position at 5. So 6. I guess. Okay. So with this kind of picture in mind, okay, we can understand that the answers to these parts okay, so you can see here that its position at 4 seconds we already got. Its position at 8 seconds we already got. Okay. Its displacement from 0 to 4 seconds that will be I cap plus 2j cap in meters, and hence the magnitude of this displacement will be root 5, whereas this displacement from 0 to 8 seconds will become 2 I cap plus 4j cap, and the magnitude of this displacement will be root 20, whereas the displacement from 4 to 8 seconds will be I cap plus 2j cap. This will be the values. Okay, so very good, Anirudh and Kirti, your answers are correct. Now the next type of question, so hope this is clear to all of you. Another type of question is sometimes where position is given as an instantaneous value. Okay, so another type of example is where a particle moves such that its instantaneous position so what we mean by instantaneous position is the position at an instant t equal to t. Okay, so basically its position as a function of the instantaneous time t. So its instantaneous position is, let's say like this, it is 2 plus 3t I cap plus 2t square j cap plus 4k cap, okay, where all the components are in meters. So find its displacement S and magnitude of the displacement from 0 to 1 second, 1 to 2 seconds. Okay. And we'll also find its instantaneous displacement S as a function of time. So what we mean by the term instantaneous displacement now is basically the displacement from 0 to t. That's what we mean by the term instantaneous displacement. Okay, so let's work this question out. So when we are expressing a vector quantity as a function of time, it's nothing very different actually. It's just like regular functions of time, but it's a vector quantity, so it has components, and each of the components will be in turn a function of time. So you can see the position vector is xi cap plus yj cap plus zk cap, where each of those are a function of time. In this case, of course, you can see that the z component is not a function. In fact, it's a constant. So that also tells you something about the type of motion that is happening. It is what we call a two-dimensional motion. It's not a three-dimensional motion. It is happening in a plane that is parallel to the xy plane, where the z coordinate is 4 everywhere. So if you just draw a plane which is parallel to the xy axis, but 4 units above it on the z axis. So the whole motion of this particle is happening on that plane, where every point on that plane has a fixed z coordinate, z equal to 4. Okay. So if you just draw your xy coordinate axis on your table and your z axis is going vertically upwards, so you can imagine a plane which is above the table at 4 units. So that is the plane at which z is equal to 4. So this entire motion is happening in that plane, because your xy coordinates are changing. but your z coordinate is fixed at z equal to 4. Okay, people, I'm going through your answers. Keep the Anirudh. Right. So all seems correct. So let's go through this again. So for the first part, you want to find the displacement from 0 to 1 second. So displacement from 0 to 1 will be the position at 1 minus the position at 0. So you can see the position vector at 0, just substitute time as 0, is 2i cap plus 4k cap. And the j cap component is 0. Whereas the position vector at t equal to 1 second is 2 plus 3, that's 5i cap plus 2 into 1 square, so that's 2j cap plus 4k cap. Okay. So the displacement from 0 to 1 second is 3i cap plus 2j cap. Okay. And its magnitude is square root of 30. So like that, now the B part, displacement from 1 to 2 seconds is position at 2 minus position at 1. So position at 2 we have to calculate, position at 1 we've already done above. So substitute time as 2 seconds in the position vector equation. So 2 plus 6, so that's 8 I cap, right, plus 2 into 4, so that's again 8 j cap plus 4 k cap. So the displacement from 1 to 2 seconds will be this vector minus this vector. So 3 I cap, 8 minus 2, so that is 6 j cap. Okay, now similarly work out the second part.
sir.
Yes, Akmal, your answer is correct, and again Anirudh and Kirti, correct, very good. So for the second part, we will just find the instantaneous displacement as the position at a general time t minus the position at t equal to 0. Okay. So the position at a general time is 2 plus 3t I cap plus 2t square j cap plus 4k cap, whereas the initial position was the value of the same at t equal to 0. So that you can see. So, yeah, is okay. So in the time interval 0 to t, the displacement it makes is 3t units along the x-axis and 2t square units along the y-axis. So this is the instantaneous displacement. That is the displacement from t equal to 0 to t. So it is always as a function of time. Instead of being for a specific value of time.
So, but if instantaneous charge, you have to find the derivative of that, no, function.
Okay, the derivative is always velocity, it is rate of change. That is instantaneous rate of change. This is instantaneous value of displacement. You understand me? They are different things.
Okay, sir.
So in fact, we are coming to that definition next. The velocity. Once you've discussed about displacement, next thing we'll talk about is velocity in the vector quantities. Later, we'll also talk about distance. There are certain scalar parameters and their distance and speed, whereas there are vector parameters which are displacement, velocity, acceleration. Okay, so let's come back to the next definition now in our list of parameters. So velocity. So in general, we describe velocity as the rate of displacement covered with respect to time. Okay. Or we can also talk about it as the rate of change of position with respect to time. Because displacement is the same thing as change in position. So rate of displacement covered with respect to the time is same as the rate of change of position with respect to time. So now when we come to the proper calculus definition, we will see that there are two types of velocity. Instantaneous velocity. Okay. Or commonly we just call it velocity only. So when we use the term velocity, the default meaning of it is instantaneous velocity, which is why it is denoted by the symbol v itself. And that is displacement in small time dt divided by the time dt. Or we can say it is the displacement in a small time dt is nothing but the change in position dr during that time dt. So they both mean one and the same thing. It is instantaneous rate of displacement covered with respect to time. or instantaneous rate of change of position with respect to time. So instantaneous velocity is instantaneous rate of displacement change in position with respect to time. So for example, we saw that previous question where the position, the instantaneous position vector was given by this, no? It was 2 plus 3t I cap plus 2t square j cap plus 4k cap. So from this we had seen that the instantaneous displacement was 3t I cap plus 2t square j cap. So now you can see that for this, now the instantaneous velocity at any point of time will be this, which is one and the same thing as this. So you can see that if you go with this definition, this one, you have to substitute this s. So when we differentiate a quantity which has I cap and j cap, that is, it's a vector quantity in component form, we just apply the differentiation by the normal principle, treating I cap and j cap like constants. Okay, so it becomes differentiation applies to the x component, whole thing multiplied by I cap. Then again differentiation of the y component, the whole thing multiplied by j cap. So here the instantaneous velocity is 3 I cap plus 40 j cap, and its unit will be in meters per second, okay? Because here the position and displacement were in meters and time was in seconds, so it will be in meters per second. Okay. Now we'll also show that if you apply this definition, then also you'll get the same thing. If you differentiate this term, it makes no difference. You will come up with the same term, 3ix 40 j cap. Hence, always instantaneous displacement with respect to time is the same thing as instantaneous rate of change of position with respect to time. Okay. So make a note of this first, and remember that from now onwards, that when we just use the term velocity or the symbol v, the default meaning is that we are talking about instantaneous velocity and not average velocity. For average velocity, we use the specific term average always. So the example below also shows how you will operate the rate of change d by dt operator on a vector quantity. It's just like your regular differentiation principle, just treating I cap and j cap like two constants which are vector quantities. They are two unit vectors which are fixed.
Sir,
Yes.
so for average velocity, the time interval is big. Only that
Yes.
difference.
So average velocity will be defined like average rate of change. So it will become S by delta t, the total displacement divided by total time, or delta R by delta t. Instead of dr by dt, it will become delta. Understood?
Yes.
Okay, people, so hope the definition of instantaneous velocity is clear with this example also. Now, the second type of velocity, as we were discussing, is the average velocity. So, average velocity is always defined for a time interval. Okay. So, it is given that specific symbol, V average. Okay, so it is the total displacement in the time interval divided by delta t, or that is the same thing as delta r by delta t. Or we can say that average velocity in a specific time interval t1 to t2 will become r2 minus r1 upon t2 minus t1. So this is the average velocity in a time interval delta t equal to t1 to t2. So again, for example, we had that thing that the instantaneous position was 2 plus 3t I cap. This one. Now suppose in this I ask that find the average velocity from 0 to 2 seconds. So that would become the displacement from 0 to 2 seconds divided by the time interval. So this would become the position at 2 seconds minus the position at 0 seconds divided by 2 seconds. So we could see that this would become 6 I cap plus 2 seconds में कितना हो जाता 8 J cap divided by 2. This is in meters, this is in seconds. So the average velocity would have been 3 I cap plus 4 J cap during that time interval, 0 to 2 seconds. Okay, so now we move on to the final definition in this series of vector parameters, and that is the acceleration. Okay. So acceleration is rate of change of velocity, as you know. So acceleration also comes in two categories: average and instantaneous. So that's the word definition of acceleration, rate of change of. So instantaneous acceleration, which we generally denote with the symbol small a. Okay. It is the instantaneous rate of change of velocity with respect to time. So again, in that example, because our position was like this, it's getting boring after time using the same example, but anyhow, we'll see more examples later also. So we saw that the velocity which you can get by differentiating this was 3I cap plus 4T J cap. So now the instantaneous acceleration will come by differentiating this. So we'll take the differentiation parameter and apply it to this vector. So when you take it inside, you see the first term is a constant. So it has no x component of expression. The second term is linear in time. So it will have a non-zero but constant y component of acceleration. So in this particular case, the acceleration would have become 4 j cap in meters per second square. Because this was the velocity in meters per second. Okay, now likewise, we also have the definition of average acceleration in a certain time interval. So again, average acceleration is given by the specific symbol or average acceleration from T1 to T2 will be the change in velocity V2 minus V1. Similarly, instantaneous acceleration is also the default value of acceleration. When we just use the term acceleration alone, the default meaning is we're talking about instantaneous acceleration. Okay, so this completes the definitions of all the parameters. Now, just take another 10 minutes. I know the time is almost up, but we also started a little bit late. So what we will do next is we will come back to scalar parameters later. Okay, speed and distance. There are two other things, but we'll come back to them later. We'll discuss this later. Currently, what we'll move on to is the specific case of motion along a straight line. Or what we call one-dimensional motion. In very short form, we just call it 1D motion. So the name suggests what it means. Basically, the motion is happening along one fixed axis. So suppose the x-axis is taken along the line of motion, because as the person writing the equation, we are free to select our system of axes anywhere we like. So the x-axis we have selected is such that it's coinciding with the actual line along which the motion is happening. Okay, so the line of motion. So then what happens is that if we go with a vector notation, the position would be just given by one component. Okay, the displacement would just be given as one component. Okay, the velocity would just be given by one component. Okay, the average velocity would just be given by. So all these things, they reduce to one-dimensional vectors. So instead of using the vector notation now, what we do is we use the scalar notation. So these quantities are still vectors only. They're not scalars, but the notation is scalar because they have only two possible directions. So algebraic sign is enough to give them the direction. So the position is just given by a coordinate. Okay. The displacement is just given by a change in a coordinate. That is x2 minus x1. The instantaneous velocity is just dx by dt or ds by dt. The average velocity is just S by delta t or delta x by delta t. And likewise, so in the scalar notation, it is the algebraic sign which tells us the direction, because there are only two possible directions, along the positive direction or along the negative direction. So in scalar notation, all the parameters have algebraic sign, that is plus or minus, which indicates the direction. So we don't need the unit vector notation, because the unit vector is the same for all the parameters, because the motion is only happening along one dimension or one axis.
So you're done writing.
Yeah, finished now.
Yes, sir.
Now see, there are some additional relationships between these parameters that we can define in terms of calculus. So application of calculus and the relationship between 1D kinematics parameters. So if we say that instantaneous velocity is rate of change of position, so we can say displacement in a time interval t1 to t2 will just become integration velocity with respect to time from t1 to t2. So this second statement which I boxed, it is like the inverse of the first statement. If that one, if one quantity is derivative of the other, then the other is the antiderivative, or in a specific interval, it will become the definite integration from this to this. Okay. So for example, if I have this equation where velocity is, let's say, 2 root t, okay, along a straight line, okay, where t is in seconds, velocity is in meters per second. So we want to calculate the displacement from, let's say, uh, one, I mean t equal to 1 second to t equal to 4 seconds. So we'll just use this above definition. So we'll say that since b is equal to ds by dt, so here ds by dt is equal to 2 root t. Okay. So in a very small time dt, the small displacement ds is this much. So in the overall time, it becomes like this. Okay. So in this case, the displacement from, what is it, 1 to 4 seconds will become integration of 2 root t dt from t equal to 1 to t equal to 4. And from that, we'll calculate the numerical value. Okay. So you can write this down and complete this integration yourself and send me the answer. Okay. So this statement here is the inverse of this. So velocity is rate of change of displacement. That means displacement is integration of velocity with respect to time. Okay, very good. The answers you have sent are correct, people. So this will become 2 into t to the power 3 by 2, right? Divided by 3 by 2. And on this, we'll put the limits from 1 to 4. Okay. So you can take the 4 by 3 common outside, and it is 4 to the power 3 by 2 minus 1 to the power 3 by 2. So 4 by 3 into this will become minus 1. So 28 by 3, or approximately 9.33 meters. That is the displacement from 1 to 4 seconds. So good, you have done the calculation correctly and sent me the answers, people. Okay, so this is one important type of relation. Okay. Now the other one is that acceleration, instantaneous acceleration is rate of change of velocity. So the inverse of this is this integration. So at time t1, let's say the velocity was v1, and at time t2, the velocity was v2. So the left hand side will become v2 minus v1 is integration of a dt from time t1 to t. Or in general, we can say that dv by dt is equal to instantaneous acceleration. So the inverse of this statement is that the change in velocity is the integration of acceleration with respect to time. So this is the relation between acceleration and velocity. Also, another important relation is that this is rate of change of displacement with respect to time, or rate of change of position with respect to time. So acceleration also has this relation that it is second derivative of displacement of position with respect to time. It is something that we have discussed before also. That's another important relation. Okay. And a third relation is by application of chain rule. Acceleration can be written as this. This is our chain rule step. That dv by dt is dv by ds into ds by dt. And ds by dt is nothing but instantaneous velocity. So acceleration can be written as instantaneous velocity into ds also. Or similarly, we can also write it as v into dv by dx, where x is position, s is displacement. So we have all these additional relationships, this set and this set. So we'll conclude today's session here, people, and next lecture we will see more applications of this. Okay, and finally we'll see the specific applications of these relationships when we are talking about uniformly accelerated 1D motion. And we will see those famous three equations of uniform acceleration motion: v equal to u plus at, s equal to ut plus half at square, and the third one we'll see how they can be derived by using calculus from these relationships above. Okay, but these relations are more general. The ones we've discussed here, the calculus relationships, they will apply whether or not the acceleration is uniform.
So, so,
Yes.
so will you be prescribing the books, set of books now or the next day?
Yes. I will send you list of books. So I'll just write the reference books here. Yeah, I had forgotten. Thanks for reminding me. So for The first level is concepts of physics. Comes in two parts. So for your combined 11-12 syllabus, both the parts will be required by Dr. H.C. Verma. This is Bharati Bhavan Publications. So this book will be using for solved examples and numerical problems, both objective and subjective. But this book will not be so much useful for theory because the theory is very concise in this. So that's what the second book will be for. Physics is simply called. Okay, volume 1 and 2 again for both years syllabus. Okay, by Robert Resnick, David Halliday, and Green. So it is Biley Easton. You can get instead of the hard copy. I mean, the hardbound book. You can just get the paperback student edition. So this will be using for theory reference. Okay. The exercises in this will not be relevant to JEE level. They will be very basic formula-based questions. And a third book we'll be following, especially for revision later, is Physics for JEE Mains and Advanced. It's a 5-volume series actually. There is Mechanics 1 and 2. So those 2 volumes. Then there is so Thermodynamics and Waves. Then there is Electricity, Magnetism. And Optics and Modern Physics. So these 5 volumes cover the entire 11-12 syllabus. Okay. So this is by an author called D.C. Pandey. Okay. Arihant Publications. Okay. There is also a series for NEET, medical entrance exam. So don't get that. Get the JEE Mains and Advanced. Okay. So this is for revision problem solving. And JEE pattern exercises. And also solved examples to a certain extent, but primarily use it when you're done with a chapter and you want to do some additional revision questions. Like now you're done with vectors and calculus. Whenever you want to do some new problems for revision, you can refer to questions from this DC Pandey. Okay? So I'll be sending you the notes that will have these books. Okay.
Sir,
Yes.
which are the books which we have to get immediately?
Like see, immediately like concepts of physics part 1 will have the mechanics portion. Similarly, physics volume 1 will have most of the class 11 chapters. Okay. Similarly, mechanics 1 will have all this kinematics, Newton's laws. Mechanics 2 you will probably need by next month or another 5 weeks or so. But the thing is like if you get all the volumes together, I think you get a discounted price. So you will need them in the entire 11-12 anyway. So if you can get hold of the entire thing, then get hold of it. You get it at a discounted price. Okay. And it's nothing specific that you have to get the latest edition and all that. You can get last year or last year's volume also. If convenient, you can even get them at a use bookstore. It really doesn't matter. Okay.
Sir, and for the problems that to solve, we'll be told, or how it will be?
Yeah, like I will be giving you some recommended problem list from these books also. Even in the theory reading, there are certain passages from Rustic Halliday which I might recommend at some point of time that you read through this before the next lecture or something. Okay. But in general, it is optional. You can always go through the equivalent thing from your module and NCRT. Okay, but it's better if you follow this reference book. Okay.
So solved examples will be marked for us, which you have to solve.
Yeah, I mean, when we are completing a chapter, you can just go through all the solved examples together.
Yeah. For after the chapter.
Yeah. Or when we are doing a certain section of a chapter, so you can find the solved examples of that section and go through them.
Yes.
Okay. Okay, people, for that's it session. Okay. All the best for your remaining tests that are happening this week, exams, tests in school, whatever.
Sir, and from HC Verma, I couldn't get any problems on differentiation.
It is there in the first chapter, physics and mathematics. Okay, it's a combined chapter. It has some questions of vectors, some question of calculus, but very less number of questions. HC Verma, you basically start from kinematics. Okay.
Yes.
It will not help you so much in calculus and vectors. There are some decent question in vectors, but you have done better level questions, so you will not really find it that useful. Kinematics and Newton's laws onwards, HC Verma will be useful for you.
Okay, sir.
Okay, so that's it for today, people. Wish you all the best. Have a nice day.
So can you please show that screen which I've written? I'll just take a screenshot of it. Yes, sir. I'm done. Thank you, sir.